4x. So what's wrong with y is equal to mx plus c? So fx, which is a placeholder for the expression mx plus c, is not linear because f of 0 is not 0. And if you double it, obviously you get something. It's not twice of x, so it's not homogeneous. So right away it's not linear. But we know that is the line. What's the contradiction here? What's the equation to a line? That basically is y is equal to mx plus c. Change it to our preferred form, which is expression equal to constant. We will write it this way: minus mx plus y equal to c. It's the same equation, it's just written differently. Now look at the left hand side of that. It's not a function of one variable. It's not an expression in one variable. It's actually an expression in two variables, x and y. Now the question is it linear as an expression in two variables? But what we defined as the conditions for linearity were only for functions or expressions in one variable. So let's extend it by saying this. Let's say that if I scale both x and y by the same factor, by the same scalar, then the output should scale by the same factor. Let me redefine that as the homogeneity for multiple variables. So here I'm using only two variables, x and y, but it could be any number of variables, x, y, 0, x1, x2, x3 up to xn, any number of variables. I define it this way: if I scale all of them by the same factor, then the output should scale by the same factor. Of course, it's a generalization because it does work for just one variable too. Additivity also, let's define it in such a way that if you add the corresponding elements, f of x plus x prime and y plus y prime is equal to f of xy plus f of x prime y prime. Of course, if I had more than two x, y, z, or x1, x2, x3 up to xn, I could just extend it. So again, this is a generalization of single variable case. So again, these are definitions. I'm actually defining the conditions for linearity this way. Then let's see if f of xy, which is mx plus y, is that linear. So now scale x and y by the same factor and then look at what minus mx plus y gives you. Then you can actually see that the factor s gets pulled out. Then it does look linear as a function of two variables. As an expression in one variable, mx plus c is not linear, but as a function of two variables, the expression minus mx plus y, it is linear by our extended or generalized version of linearity. We are kind of generalizing the notion of linearity so that it applies to multiple variables. Let's move on to the additivity condition. So this was our additivity condition. We have the summation of x and x prime, y and y prime at the same time, and then you can decompose it. You do a little bit of kindergarten algebra, and then you get f of x plus x prime, y plus y prime is equal to f of xy plus f of x prime y prime. You get that. So additivity condition also is satisfied. Our generalized version of linearity conditions are satisfied by this minus mx plus y. So it is actually a linear expression in two variables, not as one variable. Okay, so by the generalized definition of linearity, the generalized conditions of linearity, I should say, f of xy equal to minus mx plus y is a linear function of two variables. To reiterate it, fx as a function of just one variable, mx plus c, is not linear. Actually, let's ask the question differently. We know that it would be linear only if c is equal to 0. So the only form in which a function of one variable can be linear is if it is in the form mx, fx equal to mx. So instead of m, let me use the letter a. Fx equal to ax is linear. A and x being members of the set of real numbers. So the only linear equation, remember, is expression equal to constant. So the only linear equation in one variable is a very simple one, ax equal to b. It's more subtle than it looks. Right, if you write the equations in our form, that is expression equal to constant, then you just have to worry about the expression part. If you actually spread it out, like expression equal to expression, then that is more complicated. Then you will have to worry about how to make it into the form expression equal to constant. So our equations will always be actually a linear expression equal to a constant, and we will not worry about non-linear equations. Alright, so let's just generalize linearity. F of x, y, we define linearity using scaling means scale both x and y at the same time. Adding means if you have multiple pairs of x's and y's, then you add them at corresponding elements. Okay, so if I have two numbers, when I want to scale both of them at the same time by the same factor. If I want to add two sets of numbers like that, I want to add the corresponding elements, the x's and the y's. That's what I want to do. So as an ordered list. So it gives you the notion of an ordering of the list. So that's what I want to do. So that actually leads to the notion of a vector. The vector x in bold letters is a vector. Okay, that is an ordered pair of numbers, x and y. When I scale it, I'm going to scale both of them. If I scale it by scalar S. I'm going to scale both of them at the same time by the same factor. If I add two vectors like that, this is a vector, this is another vector. If I add two vectors like that, I'm going to add the corresponding elements. So I'm defining an entity called vector and scaling and addition, the operations on this vector like this, so that I can use them as part of my expressions that will have a chance of being linear. With that definition, I can actually reuse my original definition of homogeneity and additivity by saying that my input now is a vector called x, but a bold x, say that this is a vector. So homogeneity is for a function of an entity called x, which is a vector. If I scale the vector by a factor, the function, the output of the function should scale by the same factor. That is homogeneity, just as it was for real numbers, except that instead of real numbers, I have a bunch of real numbers arranged in a column now, which is a vector. Additivity, also the same thing. Instead of adding two real numbers, I'm adding two vectors now, and they should add, as I defined here, the corresponding elements. And now my notation for the real numbers, I had x as a member of R, the set of numbers. Now I'm going to say the vector x is a member of Rn. There are n numbers, so that is a member of Rn. This is to say that x is a vector of n elements, and each element is actually a real number. In our definition for now, we used only two components, x and y, but it can be any number. So let's just do one more thing before we kind of wrap it up. We want to write this equation minus mx plus y equal to c in the language of linear algebra, vectors and matrices. We know what a vector is by now. It's an ordered pair of numbers. So let's define one more operation. So we had a vector which is x and y written this way. This is the only way we'll write vectors always. It's a column. We'll always try to write vectors this way. And now suppose I have a couple of elements m and 1, minus m and 1, written as in a row. I'll call that a matrix. Suppose I define an operation between these two, this matrix and this vector, such that it is this. Minus m1 as a matrix, multiplying the vector xy gives you minus mx plus y. It's again a matrix, but matrix with just one number, which is the same as a number. Or if I don't like the minus sign and the 1 here, I might call it a1 and a2 in a row, xy. So I'm defining an operation here. I'm defining a multiplication between these two entities. The first entity, I'm going to call that a matrix very soon. The second entity is a vector, which is also a column matrix. It's a matrix of one column. So I can write an equation kind of like that. And if I have more equations, not just one equation, but so let's say I had three equations. So a11, a12, a21, a22, a31, a32, those are my coefficients. I can write them as a multiplication of a bigger matrix by the same two variables by defining the matrix multiplication this way. Again, don't worry too much about this matrix multiplication yet, because we'll go through it in many different ways next week. This week I just want to introduce you to the notion that there is an entity called a matrix, which comes from our desire to be able to write equations in a compact fashion. If I call this table of 6 numbers here a matrix and use a symbol for it, let's say A, then I can write this in a very compact fashion. If I call the matrix originally here minus m1a and my vector xy with two components, the bold letter x, then I can write this equation as ax equal to c. A is a matrix, s is a vector, and equal to c, c is a constant. And if I had three equations coming from here, from the second part of my first column, a11x plus a12y is equal to b1, and so on for b2 and b3. I could again write it in a compact fashion, a times x equal to b. So x is a vector of two components, x and y, and b is a vector of three components here, b1, b2, b3. So that stands for this set of equations, not just one equation, but a system of three linear equations. And here my matrix has 3 rows and 2 columns, and I'll indicate that by saying A is a member of R 3 by 2, 3 rows and 2 columns. X is a member of R2, is a vector. R2 is a collection of all possible vectors of 2 elements, and B is a member of R3, and R3 is a collection of all possible vectors of 3 elements. So now, as you can see, the matrix A is actually a transformation. It takes a vector of size 2 and gives you a vector of size 3. So it's a transformation from R2 to R3. Later on, we'll call R2 a space, R3 a space. So it's a transformation from one space to another. It's actually a matrix. So let me just kind of recap. For our purpose, a vector is an ordered set of numbers. It's a column of numbers. A matrix is a table of numbers, and the numbers within the table can be integer, rational, real, complex, etc. In our case, we are always interested in real numbers, but it could be, instead of R, you could have C for complex numbers, or you could have a Z for integers, and Q for rational, etc. Those are all different sets of numbers. Okay, so these are different sets: real numbers, rational numbers, integers, and complex numbers. Okay, so in Sage Math, since these guys are actually double letters, Sage Math will call complex numbers the set of complex numbers, or a field of complex numbers, CC, field of real numbers, RR, field of rationals, QQ, field of integers, ZZ. This distinction is not such a big deal really, because as you know, integers are a subset of rationals, which are a subset of real numbers, which are a subset of complex numbers. It's just that we will always deal with, not always, but mostly 99% of the time, we'll be dealing with real numbers. So in a matrix or in a vector, the numbers will have to be of the same type, meaning if you have a real number and an integer somewhere, the integer will be kind of promoted internally in Sage Math as a real number. And if you have a complex number anywhere, all elements are considered complex. So I'm giving you a vector here. So vector here. These are three measurements, so three numbers pertaining to me, myself. This is a vector, three numbers there. What are those three numbers? Any guesses? Yeah, it is actually right there. There's my weight, height, and age. Here's a matrix. In kind of fancier language, we will call our matrices over the field of real numbers. So vectors are over the field of real numbers, etc. So this is over the field of real numbers. So it's a member of R3. This is a matrix which is a member of R4 by 3. Remember, always rows first, columns second. In general, when you generalize it, which is the way we want to do later on, X will be a member of Rn. Our matrices are going to be members of Rm by n, m rows and n columns. And when I write an equation ax equal to b, remember x is a collection of n numbers, n unknowns, okay, and a has each row in a actually translates into an equation by that matrix equation. So I have m equations and n unknowns. So ax equal to b, that's a notation for a system of linear equations, m linear equation, n unknowns. So a is a member of Rm by n, x is a member of Rn, b is a member of Rm. So A is a mapping from Rn to Rm. So it represents a system of linear equations. From now on, we'll be seeing this Ax equal to B over and over again, and we'll be actually dealing with the properties of the linear equations that it represents, its solution solvability, and what the matrix says about that, etc., etc. So we'll basically live and die by this equation. Alright, so that will be the rest of the course. And as you can see, it represents a linear transformation. Later on, much later, we will call Rn a space. It's a collection of vectors of size n, and we'll call it a space, a vector space of n-dimensional vectors. So A is a mapping from one space to another. Don't worry about it for now, but I'm just giving you a preview. Now, originally I wrote the equation, a linear equation in, what should I call it, a lowly single variable, x, as Ax equal to b, because I wanted to get to the same form and the same way of saying when we actually reach a multi-dimensional, multi-variable kind of situation. This is what's going to happen in data science. We'll have a huge matrix, say 1,000,000 rows and say 1,000 columns, which is not unusual. Though that's actually a system of linear equations, 1,000,000 equations of 1,000 unknowns. But that has this origin in this simple linear equation of Ax equal to b, but we are able to, even in the first class, extend it all the way to any number of variables and any number of equations. All right.